Hey folks, this is the fifth part of an originally three-part video series on category theory. In this video, we're going to look at monads and some of their applications in computer programming. I must admit that I hesitated for some time before creating this video because seemingly everyone and their grandmother has already made a monad tutorial, and I wasn't sure it was worthwhile to make another. However, some of those grandmothers are surely now dead, and what better way to honor their memory than with a video about monads? Put simply, monads enable composition in context. If you don't take away anything else from this video, take away that slogan. It's such a good slogan, it should be trademarked. Maybe I'll use it for a paper or book title someday. Anyway, a little more specifically, a monad is a type of object which allows us to conveniently compose operations in some context. What that context is depends on the monad. We'll start by walking through an example in detail to get a feel for this. In the category of sets, functions are single-valued. Corresponding to each input value in the domain of a function, there's a single determinate output value in the codomain. An interesting question is, how can we model non-deterministic functions, which may output different values for the same input? One way is to use functions which output sets of values. A function f from a set A to the power set of a set B, that is, the set of all subsets of B, can be viewed as a non-deterministic function from A to B, which for each input x in A, outputs different values y in a subset of B. Here f of x is the set of possible output values for the input x. As an example, the function f from the real numbers to the power set of the real numbers, which maps an input x to the open interval from x to infinity, can be viewed as a non-deterministic real-valued function, whose output is some number greater than the input number. One question that immediately arises is, given an ordinary deterministic function, how can we make it non-deterministic? The answer is that we can compose the function with the singleton function, which maps an element to the singleton set containing it. Notice how the singleton function wraps a value in a minimal non-deterministic context. It can also be viewed as a non-deterministic identity function. This perspective will be useful later. Another question that arises is, given two non-deterministic functions, f from A to B and g from B to C, how can we form a non-deterministic composite g after f from A to C? We need to think for a moment about what that would even be. Intuitively, for an input x in A, the composite g after f may output any possible value of g of y for any possible value y of f of x. Let's see how we can implement that. Formally, we're given functions f from A to the power set of B and g from B to the power set of C. So we can't immediately compose f and g as is. The key is to recall from the prior video on functors that the power set operation is a functor which can be used to lift the action of g from elements of B to subsets of B. P of g, which maps from the power set of B to the power set of C, is defined by this rule. It just applies g to each of the elements in a subset of B. We can form the composite of f with P of g as seen here. Let's think about how this composite works. For each input x in A, f produces a set of possible output values. And for each of those output values, P of g produces a set of possible output values. So the composite produces a set of sets of possible output values. To form the non-deterministic composite, we need to collect all of those possible output values together with a function taking us from the power set of C back down to the power set of C. For this, it's union to the rescue. For a collection of subsets of C, the union over the collection is the set of elements in any subset in the collection, which is a subset of C. So the union operation can be viewed as a function from the power set of C to the power set of C, which does exactly what we need. For our functions f and g, we can now form the composite seen here. This is the non-deterministic composite of f and g. I recommend pausing the video and working with a few concrete examples to get a feel for this. We'll also present an example a little later. We observe that the singleton and union operations are well behaved. First, the two operations play well together. If we start with a set, like the unordered pair of x and y seen in the middle here, and take the singleton of each element of the set, or take the singleton of the set as a whole, and then take the unions of the resulting sets, we get back the set we started with. This is just a simple example. In general, this diagram commutes. Don't be alarmed, this looks more complicated than it really is. The set on top left is the power set of A, consisting of subsets of A. The function on top going to the right which is the result of applying the power set functor to the singleton function on A, applies the singleton function to each element of a subset of A. The function on the left going down applies the singleton function to a subset of A as a whole. Notice how we're using subscripts to distinguish the two singleton functions. The functions on the right and on the bottom take unions. The diagonal function is the identity. You should verify that the simple example on the top of the slide follows from the commutativity of this diagram. This is called a unit property because, in a certain sense, the singleton acts like a unit or identity element relative to the union. Second, the union operation is well behaved because it doesn't matter how we group or associate elements when taking unions. Here's a simple example of that. In general, this diagram commutes. Again, this looks more complicated than it really is. You should verify how the simple example follows from the commutativity of the diagram to get a feel for it. This is called the associativity property. Importantly, these diagrams do not depend in any essential way on the particular set A. From my last video, we know that means we have natural transformations. The singleton operation is a natural transformation from the identity functor to the power set functor, and the union operation is a natural transformation from the square of the power set functor under composition to the power set functor. The natural transformations make these diagrams commute. These are like the diagrams we just saw, but without the particular set A. In summary, the triple consisting of the power set functor, the singleton operation, and the union operation allows us to conveniently model non-deterministic functions in the category of sets. We can create them, even from ordinary functions using the singleton operation. We can compose them using the power set functor and the union operation, and we can enjoy them because the operations involved are all well behaved. In fact, composition is associative and unital, so we actually have a category of sets and non-deterministic functions. The triple is an example of a monad. The category is an example of a Kleisli category, which we'll say more about later. We can transport this idea over to the lambda calculus, which we introduced in prior videos. First, recall from the last video that for a category C, the functor category C to the C has as objects functors on C, and as arrows, natural transformations between those functors. In particular, for the category of types and functions in the lambda calculus, the functors are functorial types, that is, types that can be mapped over. And the natural transformations are polymorphic functions, that is, functions that don't depend upon the type parameter. For example, the list type is functorial because we can map a function over a list, and the reverse function is polymorphic because it doesn't depend upon the type of the elements in the list. We can model non-deterministic functions in the lambda calculus using functions which return lists of values. For types A and B, a function from A's to lists of B's can be viewed as a non-deterministic function from A's to B's. Instead of the singleton and union operations, we use the polymorphic functions return and concat, seen here in Haskell. The return function wraps a value in a singleton list. Note it has nothing to do with the return keyword in other programming languages. The concat function concatenates all the values from a list of lists into a single flattened list. It shouldn't be shocking to you at this point that the triple consisting of the list type together with the return and concat functions is a monad. Here's an implementation in Haskell. We define the return function in the obvious way. We define the monadic non-deterministic composite of two functions f and g using concat and map in exactly the same way we did using union and power set in the category of sets. From these two primitives, other monadic operations can be defined. So the list monad allows us to compose non-deterministic functions. Here's a concrete example in Haskell. The function f returns either plus or minus its input. The function g returns either 2 or 3 times its input. The function h is the non-deterministic composite g after f. Then h of 3 returns any of the values 6, 9, -6, or -9, as you can verify. It's also possible to sprinkle syntactic sugar on this with things like do notation or list comprehension notation, but we won't bother doing that here. Non-determinism is useful for problems that require exploring a space of possible solutions, like searching subsets or trees or graphs. As a simple example, here's a slick way to compute a power set, or should I say power list, using non-determinism. We define a non-deterministic predicate function which returns both true and false for every input. When we non-deterministically filter a list with the predicate, we get every possible sublist back. Notice here we're using the special monadic filter function, not the normal filter function. As an exercise, you might think through how you would implement the monadic filter function. There are many other monads out there. Each monad allows us to compose operations in some context. So far, we've explored the context of non-determinism. In JavaScript, a promise is essentially a monad which allows us to conveniently compose asynchronous operations. Here's an example function which fetches the profile text for a user by username on some platform. Since the platform itself is fictitious, let's just call it X. The trouble is that the function first needs to fetch the user's ID from one API endpoint, and then fetch the profile text from another endpoint using the ID. Neither the fetching nor the response parsing are instantaneous. They're asynchronous operations. The promise interface provides a nice way to organize the code which avoids a deeply nested chain of callbacks. The promise then method performs monadic composition. More accurately, it performs what's called monadic sequencing or binding, but that allows you to compose asynchronous operations. The promise resolve function is just the monadic unit, which wraps a value in a promise. The code here is still bad because it doesn't do any error handling, but I wanted to keep the example simple. Again, we can sprinkle syntactic sugar, in this case using async and await. This makes the code read like synchronous code, although it's still asynchronous and equivalent to the code on the previous slide. Before leaving this example, I ask that you please spare me any angry comments telling me why promises are not actually quite monads, technically speaking. I know, but they're monads in spirit, and it's not my fault that life is sometimes a little messy. Other applications of monads in programming include failure and error handling, logging and tracing, preservation of state, handling of side effects, and more. Some of these are more commonly found in purely functional programming languages, but the monadic pattern is still useful in other languages as well, as we've just seen with JavaScript. At this point, we now have the perspective we need to formulate general abstract definitions. A monad on an arbitrary category C is a triple T eta mu, where T is a functor on C. Eta and mu are natural transformations. Eta, called the unit, mapping from the identity functor 1 to T, mu, called multiplication, mapping from T squared to T, and these unit and associativity diagrams commute. It's important to see that this definition is just a straightforward abstraction of the examples we saw earlier in the category of sets and the category of types in the Lambda calculus. Now let T be a monad on a category C. Then the Kleisli category CT has for objects the objects in C. On the other hand, an arrow from A to B in CT is an arrow from A to TB in C. The identity arrow on A in CT is just the component of eta at A in C. The composite of two arrows in CT is the composite seen here in C. Again, this is just an abstraction of the composites in the examples we saw earlier. The Kleisli category is the category in which we compose arrows with the additional context provided by the monad. It can be easy to get lost in the abstractions with this stuff, but as I said at the beginning, if you're going to take away anything from this video, just remember that monads enable composition in context. They allow us to wrap values in a context and compose operations while preserving that context in a well-behaved way. The rest is just details. I have more to say about monads, but I'm going to save it for a follow-up video. In the meantime, if you enjoyed this video, please share it with somebody, maybe your grandmother, assuming she's still around, or like or subscribe or leave comments, preferably friendly comments, not angry comments. Thanks for watching.